Today we are discussing Bellman-Ford algorithm. This algorithm is used to find shortest path in a graph from a source node to all other nodes in the graph. Okay. Unlike Dijkstra's algorithm, this algorithm is capable of finding shortest path in a graph even if there are negative weights. Okay. Now, what happens if there are negative cycles in a graph? If there are negative cycles in a graph, then this algorithm can detect those negative cycles. See, a Bellman-Ford algorithm uses a dynamic programming approach. If there are n nodes in a graph, then longest edge may be n minus 1 nodes away from the source node. So, we use n minus 1 iterations in this algorithm. After first iteration, we get shortest path to all nodes which are one edge away from the source node. We further consolidate on it, and after second iteration, we get shortest path to all nodes which are two edges away from the source node, and so on. So, we continue until n minus 1 iteration. See, in every iteration what we are trying to do? We are trying to relax every edge, okay, and we will try to relax every edge n minus 1 times. Okay. Now, let us see how the algorithm works. See, input is a connected graph G with n nodes. Okay. So, we start our algorithm, we initialize a distance 0 to the source node and infinite to all other nodes. Okay. Then we are repeating our step number 4 n minus 1 times, since we are having n minus 1 iterations. Okay. Now, for each edge u v w, okay, for each edge u is the source, v is the destination and w is the weight. So, for each edge u v w, if distance up to v is greater than distance up to u plus w, then what do? We update distance up to v. Okay. So, now our new distance up to v becomes equal to distance up to u plus w. W is the weight of that particular edge. So, what is this? We are trying to relax that particular edge. Okay. So, how many times will we be doing it? Since we are having n minus 1 iterations. So, for every edge we will be doing step number 4 n minus 1 times. Okay. And after step 4, ideally we come up with a solution. Okay. But if there is a negative cycle, okay, then we can detect that negative cycle using our step number 5. Okay. So, what happens? Ideally we are able to relax all the edges, okay, using our n minus 1 iterations, but we are running one extra iteration here, for we are again checking each edge. And what are we doing? We are just checking if dv, distance up to v, is greater than distance up to u plus w. Okay. So, now we will not be updating because we have already done our n minus 1 iterations. So, this time if my distance up to v is greater than distance up to u plus w. So, it means that there exists a negative cycle. Okay. So, we are able to detect that negative cycle. So, now let us implement our Bellman-Ford algorithm on this directed weighted graph with some negative edges also. Okay. So, first of all, what do? So, we are having nodes A, B, C, D and E. So, what will we do? We will assign 0 to A and we will assign infinite to all other nodes. Okay. Now, we start our first iteration. So, we are seeing what are the edges starting from A. From A I have an edge to B. Okay. So, distance of A is 0 and weight of this edge is minus 1. So, now see if I add minus 1 to 0. So, it becomes minus 1, minus 1 is smaller than infinite. So, I will be updating it to minus 1. So, now distance up to B has become minus 1. Similarly, there is an edge from A to C, and what will be the new distance? 0 plus 3. So, now I will be writing 3 here. So, there is no more edge from A. Now, we see from B. What are the edges from B? From B I can go to C. See, the distance up to B is minus 1, and if I go to C, so I will be adding 2 more to it. So, the new distance of C will become 1, since 1 is smaller than 3. So, I am replacing 3 by 1. Okay. Where else can I go from B? From B I can go to E also. See, the distance up to B is minus 1, and weight of the edge BE is 5. So, minus 1 plus 5 becomes 4. So, now this infinite will be replaced by 4. Okay. Any other edge from B? No, there were only two, one to C and one to E. Now, what do? We go to C. So, what are the edges from C? From C there is no edge. So, now we will be going to D. See, D has assigned a distance of infinite. So, from D we cannot improve any, we cannot relax any of the edges, because the distance assigned to D is infinite. So, now we go to E. What are the edges from E? From E I can go to D. So, distance up to E is 4, and if I go up to D, so I add minus 2. So, now the new distance of D becomes 4 minus 2 means 2. Okay. Where else can I go from E? I can go to B. See, E is having a distance of 4. So, 4 plus 1 will become 4 plus 1 will become 5. Okay, which is greater than minus 1. So, there will be no updation. So, this is end of our first iteration. So, after first iteration, what are the things? A is having a distance of 0, B is having a distance of minus 1, C is having a distance of 1, D is having a distance of 2, and E is having a distance of 4. Okay. So, now we start our second iteration. First of all, we see what are the edges from A. From A there is an edge to B. So, 0 minus 1 is minus 1, it is already minus 1, we are not improving anything. There is an edge to C, 0 plus 3 is 3, but 1 is smaller than 3. So, again we will not update anything. Now, we will see what are the edges from B. From B I can go to C, and the distance up to B is minus 1. So, minus 1 plus 2 becomes 1. So, C has already been assigned 1. So, there will be no change. From B I can go to E. So, distance up to B is minus 1 plus 5 is 4. E has already been assigned 4. So, I will not change anything. From C there are no edges. So, there is no change. Now, I go to D. What are the edges from D? From D I can go to B. Okay. So, the distance up to D is 2. Now, if I go to B, so I will add 1 more to it. So, it will become 3, but B has already been assigned a distance minus 1. So, there will be no change. What is the other edge from D? From D I can go to C. See, distance up to D is 2, and I will be adding minus 4 to it. So, it will become minus 2. So, the new distance up to C is changing. Earlier it was 1, now it is becoming minus 2. Okay. Now, we will be going to E, because there are no more edges from D. So, now we are checking E. Okay. What is the distance up to E? Distance up to E is 4. If I want to go to B, then I will add 1 more. So, it will become 5. So, there is no change, because B is already having a distance of minus 1. Now, from E I can go to D. Distance up to E is 4. So, I will be adding minus 2 to it. So, distance up to D will become 2, it is already 2. So, there will be no change. Okay. So, now this is end of our second iteration. So, after second iteration, what are the things? A is having a distance 0, B is having a distance -1, C is having a distance -2, D is having a distance 2 and E is having a distance of 4. Now, what do? We start our next iteration. We start from A. See, from A we can't change anything because distance from A to B is -1, it is already -1, distance from A to C is 3, but we have already assigned -2. So, there will be no change since -2 is smaller than 3. Now, let us see, can we change anything from B? See, distance up to B is -1. So, from B if I go to C, -1 plus 2 will become +1, but C has already been assigned a distance of -2. So, there will be no change. From B I may go to E. So, distance up to B is -1, I will be adding 5 to it. So, distance up to E will become 4, it is already 4. So, there will be no change. Now, let us consider C. From C there are no outgoing edges from C. So, I won't be able to change anything. Now, let me go to D. Okay. Distance assigned to D is 2. Now, if I go from D to C, then 2 minus 4 becomes -2, but C has already been assigned -2. So, there will be no change. Now, if I go from D to B, so distance up to D is 2. So, 2 plus 1 is 3. So, but 3 is greater than -1. So, I won't change anything. Okay. Now, what I do? I will be going to E. So, what are the distances from E? See, distance up to E is 4. Now, from E if I go to B, so I add one more. So, distance up to B becomes 5, but I have already assigned a distance -1 up to B. So, I won't change. Now, distance up to E is 4. If I go to D, then I add -2 to it. So, 4 minus 2 is equal to 2. D has already been assigned a distance of 2. So, there will be no change. So, it means that in our third iteration there is no change. Okay. So, when things stop changing, when we stop relaxing edges, it means we have reached to the solution. It means in next iterations also nothing will change. Okay, because ideally we require 4 iterations in it, but since in third iteration nothing has changed. So, in fourth iteration also things will remain as it is, and these are our final distances. Distance up to B is -1, distance up to C is -2, distance up to D is 2 and distance up to E is 4, and all these are shortest distances from A. Now, since in third iteration nothing changed, so nothing will change in fourth iteration also. So, if we go to our step number 5, so in step number 5 also this condition will not get satisfied. What is the condition? dV greater than du plus w. This will not get satisfied for any of the edges in step 5. It means we are not having any negative cycle in our graph. Now, let us consider one more example. This is also a weighted directed graph and we have one negative edge also in it. So, let us apply our Bellman-Ford algorithm on this particular graph. So, there are 3 nodes A, B and C. So, A is the source node. So, it will be assigned a distance 0 and all other nodes will be assigned distance infinite. Okay. So, now we start our first iteration from A. What are the neighbors of A? From A I can go to B and see the weight of this edge is 6. So, 0 plus 6 becomes 6. So, now I will say update this distance. Earlier distance up to B was infinite, now it has become 6. It means now what we have done, we have relaxed this particular edge. Okay. Now, is there any more edge from A? No. So, now I will go to B, I will see what are the edges from B. Now, from B there is an edge to C. Okay. Distance up to B is 6 and weight of this edge is -12. So, 6 minus 12 Okay, 6 plus minus 12 is equal to minus 6. Okay. So, now minus 6 will be assigned to C. Now, we will see what are the edges from C. From C I have an edge to A. See, the distance up to C is minus 6 and weight of this edge is 3. So, minus 6 plus 3 is equal to minus 3. So, now this distance will be updated because minus 3 is smaller than 0. So, this becomes minus 3. So, this is end of our first iteration. Since there are 3 nodes, so we will be having 2 iterations. So, after first iteration what are the things? A, B and C. A is minus 3, B is 6 and C is minus 6. I will again start from A. From A I can go to B, okay, and the weight of the edge is 6. So, minus 3 plus 6 will become plus 3. So, plus 3 is smaller than 6. So, I will be updating it, I will be writing 3 here. Okay. Now, what are the edges from B? From B I can go to C. Okay. So, the distance up to B is 3 and weight of this edge is minus 12. So, 3 plus minus 12 will become minus 9. Okay. So, C is earlier having a distance of minus 6. Now, what we will do? We will change this minus 6 with minus 9. Now, from C where can I go? I can go to A. Okay. So, distance up to C is minus 9. So, minus 9 plus 3 will become minus 6. So, now I will update it, minus 6 is smaller than minus 3. So, I am updating it. So, after 2 iterations, what are the things? A has become minus 6, B has become 3 and C has become minus 9. Okay. Since there are 3 nodes, so we have done 2 iterations. So, now we will be doing one extra iteration to check any negative cycle. Okay. And in that iteration for every edge we will be checking this, is D of V greater than D of U plus W. Okay. And suppose my edge is like this, this is U, this is V and this is W. Okay. So, if this is satisfied, it means there is a cycle. Okay, we start with we start from A. So, our U becomes A. So, what is du? Du becomes minus 6. Okay. And suppose we are going from A to B. So, W becomes plus 6 because weight of that edge is 6. So, I am writing it plus 6. So, minus C plus 6. What is dV? Distance of V. So, what is the distance assigned to B? Distance assigned to B is 3. So, is 3 greater than minus 6 plus 6, because minus 6 plus 6 becomes 0. Is 3 greater than 0? Yes, 3 is greater than 0. Okay. So, this condition is satisfied for the very first edge. Since this condition is satisfied, it means this particular graph is having a negative cycle. Okay. So, we do not have any solution, but we are able to find out that this particular graph is having a negative cycle. So, now let us see what is the time complexity for Bellman-Ford algorithm. See, number of vertices R V, number of edges R E, okay, and we try to relax every edge how many times? V minus 1 times. So, how will we calculate time complexity? V minus 1 into E, and this will become big O V E. Okay. So, this is time complexity for Bellman-Ford algorithm. See, let us take an extreme case. Suppose this is a complete graph. So, if it is a complete graph, then how many edges will I have? N into n minus 1 divided by 2. Okay. So, these are the edges and how many vertices are there? N. So, n into n minus 1 divided by 2. So, what will be the time complexity? So, it will be of order n cube. Okay. This is when I have a complete graph, when I have edges from every node to every other node. Okay. Then this is the time complexity. So, now in next video we will be having a comparison of Bellman-Ford algorithm and Dijkstra's algorithm.